Okay, in fluid mechanics, especially when we are dealing with fluid statics, it is very important for us to understand pressure. Okay, so pressure by definition is normal force exerted per unit area. So you have a space and A area, the normal force. Okay, so P is F over A. So the unit for pressure is Newton meter square. Or another unit for this, which is we will normally see in fluid mechanics textbook, is Pascal. So 1 Newton meter square is equal to 1 Pascal. And it is also good for us to take note that some textbook is using bar. Okay, so 1 bar is equal to 100 kilo Pascal. If the question give you in bar, the unit for your pressure in bar, then change that to kilopascal by multiplying the value with 100. Okay, so from the definition, if we understand that pressure is normal force exerted by a surface area, so we know that if you compare this A with B, okay, from the diagram, obviously you can see that B is slightly chubbier, okay, than A. So the pressure acting at their feet, okay, assuming that they are having the same size of feet, okay, pressure exerted by B is bigger than P pressure exerted by A. Okay, because B having higher force while A having smaller force. Okay, next, in our application, we use pressure gauge to indicate the pressure of an object. Okay, if you see, this pressure gauge can be normally seen at your fire extinguisher tank. Fire extinguisher tanks look like something like that. Okay, you have a very small gauge, okay, located at the top of the tank. Okay, that gauge give the show the value of the pressure inside the tank. Another place where you can also see pressure gauge is your gasoline stand. It can be Petronas or Shell, okay, where you pump the air to your tires. Okay, that is called pressure gauge, a device that indicate the pressure of the object. For your information, gauge is an obsolete spelling for pressure gauge. We are still using this in most of our fluid mechanics textbook, and even in our class we will stick to this spelling. Okay, but this gauge is actually the same with more letters or recent spelling, which is gauge. Okay, so both are referring to the same thing, but in my class I will stick to this spelling following your textbook. Okay, pressure can be divided into 3 types of pressure. You have P absolute equal to P ATM plus with the P gauge. Okay, so at most P ATM is the atmospheric pressure. The actual pressure experienced by an object or by a person. And the standard value for your PATM is at sea level 101.13 kilopascal. So PATM is equal to 101.13 kilopascal, or equal to 1 ATM, or equal to 76 millimeter mercury. Okay, that is the standard pressure at sea level. Okay, PATM depends on location. Okay, if sea level, that is the value. If you are climbing mountain, higher place, for example 4,000 meter above sea level, then you will have different atmospheric pressure. In most of the question, atmospheric pressure is either given or you can find from the property table. Okay, the second pressure is gauge pressure. Okay, gauge pressure is the pressure, the difference between absolute and atmospheric. Okay, so where do you get this? Normally you can get this from a measuring device. That's why it says here, most pressure measuring devices are calibrated to read zero in the atmosphere. Okay, meaning that if you have a tank, okay, and this reading, the reading there shows that it is 70 kilopascal. Okay, that gauge shows the pressure inside the tank only, because initially this gauge is being calibrated to 0 kilopascal, which is at sea level. But we know just now that at sea level we always have this pressure acting on us. Okay, but this gauge is being calibrated to 0 kilopascal. So the 70 kilopascal shown at the gauge is actually 70 kilopascal only inside this tank. Okay, so with that, the P absolute of your tank there is equal to P gauge plus PATM, which is 70 is the gauge, and that is at sea level plus 101 kilopascal. So you will have the absolute pressure there is equal to 171 kilopascal. Okay, so as you can see here, we have absolute pressure 0, and then that is our ATM, which at sea level is 101.13. Okay, then this is the 70 kilopascal from our example here. Okay, so the absolute pressure of the liquid inside the tank is 170, but the reading at the gauge only shows you this reading. Okay, pressure at a point. Now, if let's say you have an object, okay, and it says that the liquid inside this object, this tank, is 70 kilopascal. Okay, so Pressure is a scalar quantity. It's not a vector. So the pressure acting at this surface, because by definition P is equal to F over A, right? So acting at this surface, pressure acting at this surface, here and here, this is considered a particle, okay? Is always the same, 70, 70, 70, regardless the direction of the pressure, because pressure is not vector. Okay, pressure does not affected by the direction, but it's affected by the depth. Okay, so how do we know that? Because pressure is being quantified as P equal to gamma H, in which gamma is equal to rho G H. This part, go back to section 2.2 or video 1 if you're not sure what is gamma. Okay, so here we see our first equation. P equal to gamma H or equal to rho G H. Unit is kilopascal. So from this equation, we know that your pressure is a function of the density or the specific weight and also H. Okay, so pressure will change if you change the fluid or if you change the height. Okay, that's why pressure varies with the depth and also varies with the density. What does it mean by that? Okay, we go with this diagram. For example, you have the blue color is water, and down there you have mercury, the grey color. So you have two layers of liquid. Now, P is equal to gamma H. Okay, so we take one horizontal level first, which is here. On this line, on this horizontal level, you have points A, points B, points C, D, E, F, and G. Okay, are those points acting at the same H? The answer is yes. Okay, are those points acting in the same liquid, which means the same density? Yes. Okay, so PA is equal to PB equal to PC equal to PD equal to PE equal to PF equal to PG. Okay, as you can see from the diagram, even though PA is being separated by B by an obstacle, okay, it's still having the same pressure as long as it's in the same liquid like this, connected with the same liquid, and is on the same horizontal level. Okay, so the shape of the obstacles between those points does not affect the pressure at point D, E, F, and G as long as it's on the same horizontal level. Now we compare point H here with point D. Okay, we compare PH with point D. Okay, does these 2 points acting in the same liquid? The answer is no. H is acting in mercury while D is acting in water. So obviously the density is not the same. Okay, so pH is not equal to PD. Okay, next. If let's say we compare another point, we create a new point here. between D and E, we create point J, okay, point J. Okay, so PJ with PH, it's on the same vertical line, okay, but is it in the same liquid? No, okay, because H is in mercury and then J is in water, so the density is not the same, so not the same. And of course the second part, your H, is not the same as well. Okay, next we try to compare another point. We take G and I, okay, PG, PI. Are these 2 points acting in same liquid? Yes. Okay, both are in water, so density is the same. But are these 2 points acting on same elevation? No. G is higher than I, so it's not the same. Okay. Next, we compare points H and I. PH, PI. Okay. Is it in the same liquid? No. One is H in mercury, while your I is in water, so the density is not the same. Even though the H is the same, it's on the same horizontal level, H is the same H, but density different, so it's not the same. So with that, you can conclude that pressure is the same at all points on a horizontal plane in a given fluid regardless of the geometry, provided the points are interconnected by the same fluid, homogeneous fluid. Okay, so we have covered one important equation here. P is equal to gamma H, or rho G H. Okay, so pressure varies with height, the depth, or the elevation. Now, if you take one datum point where the H is equal to 0 meter, if your fluid or the H going upward, then the pressure decreases. Okay, if the depth increases, meaning that the H going downward, so the pressure increases. Okay, if you go up on a mountain, this is a mountain. If you go up, pressure decrease. If you go down the sea, deep into the sea, then pressure increases. So that is the first important equation. But there is one exceptional case. Okay, if you take air and compare that with liquid, okay, gas with liquid. Okay, in liquid, the pressure is very dependent with the height. Okay, so if let's say you have a container like this filled with water, with any liquid, the pressure at this point here would be different from the pressure below there. Okay, if this is 0.1, here is 0.2, P1 is not equal to P2. This is the concept that we have done here just now. Okay, where you have P equal to gamma H, the liquid is the same, it's the same blue liquid, so you have same density, but the H is different, so P1 is not equal to P2. But an exceptional case for gases, especially for air, Okay, for air, the variation of pressure with height is negligible. Up, I can say up to maybe around 100 meter. Okay, there is no exact height being defined, but if the elevation is very small, okay, then we can neglect the pressure different between one point and another point. Please excuse my voice, okay? I'm having a very terrible flu. Okay, coming back to this, assume that you are in your bedroom, okay? There's height difference in your bedroom, and this is you in your bedroom, and that is your ceiling, okay? And maybe the normal height for a house is 4 meter. There's the elevation difference between this point and here, okay? H1 is 0, H2 is equal to 4. By definition, P equal to gamma H. So H at point 1 is equal to, if we make it as 0, then it will be difficult for you to see the difference. Let us. Okay, we change that. We take a point here. PH there equal to 2 meter. So that is 2 gamma, and at point 2 is equal to 4 gamma, in which your gamma is the same. You have air. Okay, by definition, we can say that P2 is equal to P1. P2 is not equal to P is not equal to P1. Okay, by definition. But this is an exceptional case for gases with relatively low height difference, low elevation difference. Okay, P1 is equal to P2 because the density of air is approximately the same. Density at this point here with the density, still imagine you are in the same bedroom, okay? Density at somewhere near the floor and density somewhere near the ceiling is still the same for air. Okay, that's why P1 is equal to P2 for most of the cases when it involves air. Okay, but of course that does not apply to a situation where you have a very significant elevation difference. For example, you have a ship, okay, and you are diving deep down the sea. There you go. Okay, and this is water. Okay, not a good example. We go, instead of going for diving, we go to mount climbing. Okay, because we are looking for air as our fluid. You are here, you're climbing Mount Kinabalu, approximately 4,000 meter. Okay, so obviously the density when you are at sea level is not the same when you are at the peak of the mountain. Okay, in that case, this is point 1, at the peak is point 2. P1 is not equal to P2 for air only. Okay, remember this. Okay, with that we are done with the introduction for your pressure.